Good afternoon, class. So first of all, I just am very grateful for this first day of this symposium. I'm sure I speak on behalf of all four organizers, Jade, Marco, and Marek. I can only imagine the rest of the week given today. And I also want to thank our exceptional chairs. Uh, You know who you are. All right, so I promise, one of the things that we discussed over lunch, and obviously, to bring all of you together to discuss all of these topics in 5 days, and to, represent the areas, to represent the different groups worldwide, et cetera, to give everyone a chance to speak, essentially, however short. Um, even with some time in the schedule that does not allow for ample discussion at the end of every presentation. So the other thing I wanted to mention is it was also impossible we have lectures and then we have invited talks to cover, pick up where the lectures have left off, and then we have contributed talks and posters to get into more details and more technical aspects. And it was impossible to schedule those in such a way that you would see the lecture, then the invited talks, and the contributed talks in sequence. So we've been, on the theory end, we've been a bit sequential today, although there's more theory tomorrow, but we've jumped ahead on some other topics. So having said that, just bear with us as we go through, and we hope to, as we go through, fill in any gaps. So what I'd like to do today, and I think we'll try to do this. Yeah. Oh, yeah. Thanks, Jade. What I'd like to do today is I promised I would open up the discussion since we have ample time, he says, laughingly. I wanted to open up the floor to questions that were not addressed today that came up during the talks. There were people who raised hands, and we were not able to allow them to ask their questions. We had to forge ahead. So I thought we'd start with that. That's a good way to initiate discussion. If needed, I think it's fine if we have a presenter, come down and plug in and show something to respond to any questions that come up now before we get into some of the overarching questions of the day, which I've listed some of them here, and of course open up the floor later to you to tell me what I've missed. So are there any questions that came up today during the presentations by Bernard and Thomas and others who followed that you'd like to raise now, that we would like to speak to now? Please feel free. Don't be shy. David, yes. Christine, go ahead. I think you do need a mic, and I'm hoping, given my injured knee, that they're not expecting me to run it up to you. Yeah. Yeah.
Testing. Okay. I have a question for David's talk this morning. Hi. So you showed like a spectrogram where you had I remember on that page you had like a non-exploding model and an exploding model. And then for the exploding model specifically, you showed like a kind of a spectrogram where there's like the high frequency component like splits into two, like where you've got like I think FP mode and G mode like in two separate like it's like a very obvious thing. So usually, based on my understanding, I'm still like pretty new in this area, like the high frequency is usually like one single streak where you can't really tell apart the different modes. So can you explain why for that model or whatever you're showing, there's like this split?
Yeah. So,
yeah. Thank you.
You want to show something? That's fine.
Yeah.
Yeah, come on. Come on down. You're UHBC, right? Yeah. Oh, okay.
Yeah.
You want to share it through Zoom? That's fine.
Yes.
Thanks, John. Good idea. Yeah, and I should share mine through Zoom, right? We have some people on Zoom. Okay. Marek will have to give me that, so we'll. I think you're up here, dude.
This right. Was it this figure? Okay, excellent. Yeah, so for this 23 solar mass per gender on the top right, we see this, we call this like a fan. There might be another word in the literature that we use, but this high frequency point that rises and falls that corresponds with the onset and the decline of accretion between a third of a second, roughly a second. And afterwards, we see a persistent F mode as the PNS shrinks, the frequency goes up. But this sort of this shark's tail, I guess, or even a fin, is the beginning and end of accretion. And then afterwards, we see an F mode and we see persistent P modes at high frequencies. Yes, and that's the phenomenology here. Mhm. Yeah, but these are from simulations. These are not templated onto any detection prospects for instrumentation.
Right.
When some simulations only have like 1 million node.
Oh, I think largely, I guess, because we got to past the second. This really appears past the second, so it might be a late time manifestation. Maybe at earlier time. Yeah, that's the only answer I can guess here.
This may make a difference. We're not all using the same color tones.
Oh yeah, absolutely, yes.
So I think so certainly the P mode forest is present in some other simulations, but it may simply be visualized in a way that makes it more visible here. We'd have to look into that. I think there might not be a discrepancy.
Most of the gravitational wave signatures that Jade has collected and made available to everybody don't go up to 10,000 or 8,000 hertz. So a lot of the sampling from the actual data could be part of why you're not seeing it as well.
Yeah, and it could also be a feature from explosion and non-explosion because we don't see, like we see these clear early forming P forests, I guess that's what we're calling them now, in the black hole format, I guess the failed explosions. And you can see them early on because there is no fin rising at high frequencies, so maybe it's just obfuscated here.
Thank you, David. Are there other questions? Yes.
These are all using the spatial equation of state because that is consistent largely with.
And the power gap,
What's that?
which frequency was it in?
Yeah.
The power gaps that you were seeing, which frequency is it in?
Oh, the voided crossings, you mean?
Yeah.
They're pretty independent of mass, not exactly, but they're around a kilohertz. It was a bit higher for the 23, which is, we haven't figured out what that is, but for most models, it's around 1.2 kilohertz.
I've seen them only depending on the US before. So that's why I was asking about your US. Okay, thank you.
Very good. Okay, excellent, good. That's the way to start. Other questions that were left on the table earlier today? No, come on. Michele, please. Yeah, yeah. I think Jade's on this side.
So this is a question that I asked to Bernard, but maybe some people can comment on that. And this is regards the frequency of the SASI. I know there has been papers where people were implying that we expect the frequency in the gravitational wave to be roughly twice the frequency in the neutrino side. And then perhaps if you're along the axis of the SASI, this is not true. But then it seems that there is a little bit going back and forth on the consensus. So I don't know if any of the theorists want to comment what is the opinion now in terms of the relationship between the frequency of the SASI and the gravitational wave and the neutrino channel.
Bernard, I'm giving you the microphone.
I can give my takeaway, but someone might want to comment and make it more objective. I think the models where we have clear SASI signals, many of them have SASI features that are maybe too short to make a definite answer about that, and where exactly the band lies is a bit contaminated by how exactly we do the windowing of the short-term Fourier transforms and so on. So I think my answer is whether and to what extent some frequency doubling and to what applies, and what the actual relation to the base frequency of the SASI dipole is. I think I would just like to see more clean models, which means giving a lot of 3D models a shot and seeing which ones produce SASI. I think that's what I would like before I tie myself down to some guess of when not we have any frequency doubling.
Yeah, I would sort of generalize the statement. So in 2D, for example, when you have only the L=1, the sloshing mode, and if you're looking perpendicular to the axis, then you'd expect 2 quadrupole deformations per SASI cycle. But in 3D, it's much more complex, right? You have sloshing and spiraling mode, and you see from the explosion models that were shown earlier by several people that from at any given particular direction, you might not expect such a clean, pure doubling. I agree with Bernard. We need more studies like this, but I think there'll be a spread. It is sort of my general view on that.
Exactly. You're actually taking away the comment I wanted to make.
Oh, okay.
It's fine. I mean,
Sorry, Thomas.
No, it's absolutely fine. My question is, I mean, I didn't know that there is particular interest in that, but my question is, do you really expect that to be diagnosed from the next galactic supernova signal? Will we be able to really see those details? I mean, I'm getting old, and the older I'm getting, the more pessimistic I am. I've been waiting for a galactic supernova neutrino with a signal for 35 years already. I mean, I would be happy if in my lifetime we could actually even have only the information that there is a gravitational wave signal coming, because that would already be good to exclude a couple of quite weird and demanding and extreme issues. But do you really think we can extract frequencies of the SASI from a next measurement?
I'll let you answer, but I think I can also answer.
Yeah, I expect that it will depend on the amplitude of the signal. If we did a couple of papers on a waveform with SASI 3D from Keikutake, and in that case, we would be able to tell if one is the frequency twice the other. But I've seen other papers where the SASI was much weaker, where we would not. So all I'm saying is that it's model dependent, but we have at least one example where we think we would be able to distinguish if one is twice the other.
You want to say anything else?
No.
So,
Thomas said.
so I had a broader question off of Thomas, which was, he asked, can we distinguish, learn something about the SASI and the convective instabilities? But one of the things that I would love to have coming out of this week is, what do we want from the engine community? What do you want to constrain from observations on what we're worried about in the engine? So how do we think we can, what do we want to probe, and what do we think we can probe with, say, the next galactic supernova in all of the uncertainties in our engine? Because you throw on top of it the convection, the equation of state, the neutrino physics. What do we think we can really do with the galactic supernova to really constrain some of the uncertainties that we're dealing with? And I'm happy for anybody to answer that.
You have no idea what you just opened up.
I can talk alone, but it's really other people talk.
I mean, I can give the answer of what we think we can and we have tried to do is the main dominant emission is this ramping up mode. And we know that for a galactic supernova, you can extract what is the frequency evolution of the thing. And if you know something about the modes, how they behave, and we think we know something, but it can be improved, of course, you can infer something about the proton-neutron star. In general, it's going to be some ratio of mass versus radius, radius square, radius cube. We have done the whole process with injecting it in LIGO, Virgo noise, extract it back and try to get what is, in that case, was mass versus, over radius square. And then you compare with the simulation, and we show that you can do it for a galactic supernova. Now, how useful is that? Yes, this is mass over radius of the hot proton star. So now what is this telling you about the equation of state, about the explosion mechanism? I mean, it's telling you that there is a proton star, which is, I think, is a good start. And what else is difficult to say, yes.
I guess if there's strong SASE for a long time, it might tell you that the star hasn't exploded. Maybe if you don't see the EM signature. If the neutrinos and the gravitational waves suddenly disappear, then you've probably formed a black hole.
Time to the explosion, how long does it convect before it, yeah.
So again, kind of broad brushing and answering it on a different level too. So you saw from today's talks, and of course in the literature, Chris, you've seen this, you know this. And Bernard talked about this, and David and others talked about, what we are seeing is sort of trends, right? That, we have I would say, a pretty good understanding of the gravitational wave emission post, say, 100 milliseconds after bounce. I'll show some stuff on Friday that will point to the fact that I don't think we certainly do not know much about the gravitational wave emission before that, and the reason for that is we don't have 3D progenitors. So, but once things settle down after 100 milliseconds post bounce, you can see the picture has emerged, as Fulvio Ricci once said to me in Pasadena in 2017 at a meeting like this. He said, "You have a template." I'm glad he said that, and I didn't, because I would have been shot by a number of people in this room, right? But so I think we have an understanding of what this looks like. We have a low frequency piece and a high frequency piece that Pablo spoke to. In the low frequency piece, you can see the SASE activity there. You can see the memory activity there. In the high frequency case, you can clearly see that. And that's, of course, also very energetic, although not in the optimal frequency band like the SASE is. Now, I'll answer the question in a different way. When Mother Nature blesses us with a supernova, and the young people in the room, next time Tomas talks, you need to cover your ears. So we need to keep them upbeat, Tomas, because they have to keep going after us. We don't want to.
I said me.
Okay.
Not the others.
Right. But Tomas, everybody in the room who's a modeler will tell you this, that Mother Nature will give us an explosion. And it's the fundamental difference between being able to quantitatively match what we observe in that explosion versus all the wonderful progress we've seen in the trends, right? So the point being that to do that, the models have to advance to the stage where they make accurate quantitative predictions, or as close as one can get, for a given star. And the models are not, they're maturing. There's been a great deal of progress. You know as well as I do how much progress we have made and what we know now relative to when I started and Tomas started. I'm a little older than Tomas, to be fair to Tomas. But at the same time, the models, as I'll talk about, I'm tasked with talking about the next 10 years on Friday. the models have a long way to go before we get to that point. And there are uncertainties, of course, that are not in our control or in the control of other communities, but that doesn't mean we can't stop pushing our parts forward, right? So I don't know if that, I mean, that's an excellent question. And there's really two levels to that answer. One being, we know enough now to say yes, we'll be able to pick out the SASE and the memory and, and other things, and hopefully do some parameter estimation, as Pablo described, of the mass and radius of the protoneutron star. But at the same time, for the given progenitor that's identified through observations, our models might be wrong. So.
Because we don't know that well enough yet. So even if we say, oh, well, this is a progenitor, it's a 15 solar mass star.
That's right.
We don't know what the core looks like because we're still struggling with that. And I blame, is Marco still here? Where is he?
Yeah.
I blame him. Yeah.
He's hiding, you see. He's ducking down. No, he's not. He doesn't even know we're picking on him.
About this, but if we measure, because what we measure is the mass and radius evolution, the time evolution, and this is telling us something about progenitor structure. It's mixed with information about equation state because it's as Alejandro was saying antes, the slope depends on the equation state and also in the progenitor.
Right.
But you get partial information, and now how much information, I mean, if we were able to get equation state from other place, then we will be able to say something about the progenitor structure for sure.
In this context, I have another question about stellar cores. You're right, Chris, that's one of the big uncertainties. Would the observations be able to detect the core bound signal? Although it's just a very short, spiky 10 millisecond feature, would observations be able to find that?
I would say short and spiky is the things we're best at finding. Like, I don't know if Sergey's still here or Marek can say something about CWB.
But this information is already available.
Yes.
What is the limit of strength? Yes.
Yes, but if it's strong enough.
Yeah, but what is strong enough?
In terms of, I can tell you in terms of SNR, in terms of compared to the high frequency, that's the point. But anything that is extractable, I think in terms of, for instance, in frequency regime, it's as Jade pointed, it's not the most difficult type of signal.
Take 5 or 10 kiloparsec.
Yes.
Take 5 or 10 kiloparsec distance, yes. And let us signal to noise ratio, whatever, 8 or whatever you need, and let us know what is the amount of rotation you could diagnose and limit.
But yeah, it doesn't.
0.02 in.
Anything larger than that you can define.
Mm-hmm. That in some sense, that is the easiest type of signal. What?
Because we do not know much.
The convection is much more difficult because it's white noise.
Yeah, that's my point here, because I mean, this convection issue is very, let me say, model specific or progenitor specific and time dependent. How long does this period last before the explosion sets in? There's a lot of components. So my question in this context, and remember what you said, Pablo, is certainly well taken. What is the fundamental physics which we can really extract from the information? Yeah, there was convection. It's a bit difficult for me to recognize that. But this rotation issue, we have no way to measure rotation in the core of a star. Yeah, no way. That's all based on theory.
Gravitational waves will answer.
Yeah, I just wanted to comment that rotation has an additional problem, is that the bound signal depends on the observation angle. So if you don't know the observation angle, which is very difficult to measure, then you always will have degeneracies on any estimation. So if you don't see the bound signal, it doesn't mean that it was not rotating. It may be just the wrong angle. So there are additional problems with rotation.
So we have a hand up here, and then Håkon's been waiting for ages, so we'll go down there.
I've been reading some papers on how the rotation affects the high frequency feature. And from what I've seen, it seems that the rotation of the progenitor, the faster it rotates, the more it dampens the high frequency feature. And I was wondering if people are thinking of looking further into that, because that plus the equation of state plus the universal relations, I feel like they haven't been like coalesced into something, if they agree at all. But I think that would be a good way to parse out the rotation.
I'll let Michaela answer that. Then we'll go to your question.
I have an answer and also a related question for Martin Oppergaulinger. So the first thing that in the last few months, and I got the confirmation today, is that the shape of the first 3 peaks from a rapidly rotating seems to be a fairly robust feature that everybody gets. And the agreement I saw today on the morphology was wonderful. And so it is true, as I know, as we just heard, that the amplitude depends on the angle. But someone can say, let's take the optimal. The average you expect for all the rotation is you're going to lose, I don't know, 60%. Even if you lose 60, so it means on average, with a beta that is, meaning the ratio of kinetic energy versus gravitational potential energy that is larger than 0.02, at 10 kiloparsec, we can very clearly detect it now. So that's the first part. The second question that is of highly interest for me is that I saw some 2D papers a couple of years ago from Martin, where he was seeing some turbulent component later on that has a comparable amplitude, which would be a wonderful news for the detection range of those models. And my understanding is that the amplitude is a little bit lower if you run in 3D. So I don't know if we're going to see those waveforms in 3D, because I know we are already at the order of 50 to 70 kiloparsec for those models just with the core bounce. But if you have 1.5 seconds of that stuff after, we already would go to 200 or 300 kiloparsec. So I guess there's an answer there and a question there. Zero, yeah.
Before collapse, so in the iron core.
Yeah, and there is a paper, Laura, Claudia Moreno, that is at the door, is going to give a presentation about that paper, which is published in Classical Quantum Gravity.
Okay, you go.
Yeah, I guess this is kind of now, we have moved past this a little bit, but I would be happy if we just have a gravitational wave detection and we know that there's a proton-neutron star there. And I want to say that I really think this word that was brought up, I think Pablo said it, degeneracies, is really a killer. Because there are so many degeneracies, and I think we should be really careful with overestimating how much we can learn from a single detection, because there's degeneracies between the vacational state, between the progenitors, and observer angles, and so on and so forth. And I really wonder if we'll be able to learn I don't think we'll be able to learn anything more about the equational state than we already know, right? So just seeing gravitational waves, just knowing that there's a proton-neutron star, just knowing that it has this typical shape that we expect, we already know that we're on the right track. And I think this would be very helpful, in my opinion. Maybe a bit negative, but.
Well, yeah, it's more of kind of it kind of follows on a little bit to what you said. Are we not indeed too optimistic to think that a single one is going to solve everything, right? And my question more is, I think it's going to be an interplay between detection and then being able to observe certain features, not observing certain features, and then iterating. And so my question is more, rather than just focusing, what can we do with a single one? How do we see this progress as we, in the future, Einstein telescope, etc., see maybe more than one? And how do we also, from observation, influence the more modeling aspects that we think that we need as well? So I'm just wondering whether people have thought about that rather than just one shot and we have everything.
Marianne's pulling I don't believe you'll get more than one face. I'll bet you money we will.
Jade, I was going to comment on, was someone else ahead of me? That's fine.
No, you go next.
Okay, so to Håkan, so I think it's great if we can learn about things like the protoneutron star mass and radius and the equation of state and things like that. But just you know, the fact that we have these spectrograms from multiple groups, sophisticated simulations, basically showing these canonical features, the high frequency feature, SASE, memory, etc. I mean, that alone, right? If we have a detection and the gravitational, those who, you know, the LVK team is able to detect those pieces, that is huge. I mean, it's not just, you know, this is it quacks like a duck, it's a duck. It's much more than that, right? I mean, we have the ability now through the simulations themselves, plus the spatial decomposition, modal decomposition, all the things we heard about today, to connect, you know, between the ingredients, the central engine components and components of the gravitational wave spectrogram, right? So confirming that the SASE is there or not, you know, the memory is there or not, right? The high frequency feature, how the high frequency feature evolves in frequency, you know, which indicates how the PNS will evolve regardless of whether we can know enough to pin down individual parameters. I mean, that's the 0th order, right? Well, detection is the 0th order. That would be the first order. And then if we could get more information beyond that, that would, of course, be gravy. But for sure, with one detection, I think we understand things well enough now that we probably could pull out these pieces and say, you know, yeah, this is there, this is there, this is there. So that's my view. I take a, you know, I'm an Italian DNA, so it's a glass is half full, right?
Okay, so I have one quick comment. Like in terms of like detectability, I would maybe like tomorrow there will be whole discussion about that, and it's better to show it on the plots. And I have a question about explosion mechanism. So yeah, we can learn properties like how protoneutrons are contracts. We have SASE, but then like the fundamental question why the stars explode. In the past, there was a question like MHD driven and then neutrino driven, then now it's like slowly rapid rotation, and I just got lost in terms of what explosion mechanisms are on the market now and how to differentiate that. They saying that if you see gravitational wave, this is this mechanism against like the other mechanism.
I'm thinking of a beautiful paper that was written by Jade and Bernard recently that addressed that point. So why don't we start with you, Jade?
I guess my personal opinion is that the neutrino-driven mechanism and the magnetorotational mechanism are the only really serious ones, but there's others like, you know, the jittering jets explosion mechanism or the acoustic mechanism or whatever your favorite mechanism. But really, I think it's just neutrino or magnetorotational are the best accepted ones. And I think to be able to really tell well if the explosion was magnetorotational, we need more simulations of gravitational waves that are long duration with magnetic fields and rotation. So even though I keep writing papers about determining the explosion mechanism with gravitational waves, it's kind of like the best we can do with the waveforms that's available, but would be much better if we had more waveforms for other explosion mechanisms, because really we have loads of neutrino-driven explosions and hardly any for anything else.
So that one is still holding, the MHD versus neutrino.
Well, I think, if I may, because we have people in the room like Matteo and Martin and others, and the sense I get from all of these wonderful simulations is this. I'll summarize and then they can correct me. I mean, you know, unless you have initially very large magnetic fields, a lot of rotation, the magnetic field topology is, you know, magically aligned with the rotation axis, et cetera. So unless you have a Goldilocks situation, the supernovae will be neutrino driven. aided potentially by magnetic fields. Is that a fair statement?
I think that.
So I think the magnetorotational case will be rare, and I think when if Mother Nature does give us that one versus the other, I think there'll be very significant telltale characteristics about it, bounce signature and things like that. Of course, obviously, across the electromagnetic spectrum, we might expect jets and things like that that are going to look really quite different. But there are others in the room who've really focused on that, so they'd be better to comment on that.
May I again be the devil's advocate here?
All right,
I mean,
young people.
No, it's for the young people. I mean, I don't need to define which side with respect to the explosion mechanism I take. But all of that is based on theory. We have no observations which tell us the progenitor structure. We have no observations which tells us how much rotation there is in the core.
Right.
And I personally take these alternative suggestions, whatever they are, whether you think of the thermonuclear mechanism by Katz and Kushner, whether you think of the phase transition mechanism, whether you think of the acoustic mechanism, which has been in the literature some 20 years ago, I take them seriously with respect to challenging our canonical thinking. We have no progenitor observations. It's all based on stellar evolution theory. Stellar evolution theory is one-dimensional modeling. Nobody really tells us that these progenitor models, which were given to us by the stellar evolution modelers, are the right structures. So I think we can learn something from the bare observation of a signal coming from a supernova. The question is only, what exactly does such a signal tell us? What is predicted for the acoustic mechanism? What is predicted if a thermonuclear explosion were happening? What is predicted if this chittering jet mechanism were a feature of reality? So I think what we need in order to really do the best of a measurement is we need simulations, not just doing the neutrino-driven mechanism, which has been explored very well. And we don't need 5 other groups around the globe which do the neutrino-driven simulations and just repeat what others have done before. There's too much of the literature. Explore alternative scenarios as well and predict the signals coming from those scenarios.
I agree.
Yeah, I think I agree as well. The only one thing that I would like to add, of course, is there is a certain risk that if you explore alternative scenarios just for the sake, you get a proliferation. And it's like, yeah, for the WMAP observations, when they come out, people already have 1,000 papers for all the different alternatives in the drawer. I think what will happen to some extent, also based on the way we still ponder some of the data for the neutrino data for 1987A after many decades, is that there might be some weird features involved there that we will probably then struggle to explain, and that might constrain or point to such alternative scenarios. So one thing that I could throw into the arena for alternatives, for example, is, I mean, Thomas, from a different bent, the phenomenological bent, right? You and Stan were sort of forced to consider that, well, maybe in these stripped envelope explosions, you need some extra power at late stages, right? To put out the light curve. So the question is that something that we would also see reflected in gravitational waves? Yeah, it might be low amplitude, but perhaps it might have a signal that also lasts for a long time, despite having low amplitude, that has good phase stability. So these are things that we could think about. Is there anything that can still come in at late stages and very unexpected? I mean, the work by the Paris group on the possible dynamo signatures, that was something interesting in that direction. And maybe there's more to be found, more to be thought about.
Chris has his hand up, I think.
So, and I think there's some, so I agree with everything that Thomas and Bernard just said, but there are observations that are providing us clues into what's going on. And I'll talk about quite a few of these on Thursday, but I wanted to bring up there's these objects, these broadline supernova. We think that they have something that is different, but they also have some very peculiar specific aspects. They are only 1C. If there's any helium, it's a small amount of helium. So they're somehow, we've removed so whatever engine you're going to produce has to, explain that. It has to only work then because we don't see them in 1Bs, right? So there's observations like that we can use to try to do this. The other thing that's feature of them is they're typically not at solar metallicity. They're lower metallicity. So, when we get a model and say this is going to be the engine, there is data out there, even, there's data out there that can tell us something about, is that engine working? So I think there's more out there than just, what we think we have, if we look hard enough.
Yeah, so I want to go back briefly to the comments on identifying a signature at core bounds as indicative of rotation. I'm sure I'll talk more about this, Tony, but that could also be degenerate with 3D progenitors that are collapsing inward and also strike a signature because of convective instabilities on infall that would also manifest at core bounds. So you could have two origins, 3D instabilities or rotation as driving signatures at core bounds. And then
The bound signal comes from half a solar mass at the center of the iron core. There is no convection at the iron core.
But you do see pre-collapse signatures of gravitational waves if you evolve a 3D progenitor. Yeah, so if you're able to spatially resolve the contributions to gravitational waves, you can tell them apart. But how well can you temporally resolve pre-collapse signatures and signatures of that? But are you confident that we will be able to resolve those with a single measurement of gravitational wave? Okay. Okay. And then secondly, I wanted to also add that we're not just going to see gravitational waves from an event. If snooze is online, we will also see neutrinos. And so we can optimistically add one more point on a mass radius plot in addition to what we've seen for NICER to constrain the nuclear equation of state. We can maybe even more optimistically try to argue about the possibility of neutrino oscillations, because if you have gravitational wave detections and you have neutrino detections at the same time, you can say so much more than you have any in isolation. And then thirdly, I also think that there is a body of observational evidence that's ready for us to try to compare to in favor of the neutron-driven mechanism for core collapse or any mechanism, right? We've talked about gravitational waves, we've talked about neutrinos, but there are also light curve spectra. And I think in the last decade, there's been a transition to producing the first electromagnetic signatures from core collapse supernovae. And these could perhaps directly couple the neutron-driven explosion at the first seconds after the ENM observations at days.
You know that I have worked for 10 years on that. I mean, we did, you showed Cassiopeia A. We actually even simulated a remnant phase already of Cassiopeia A. We predict the morphology and so. But the people who challenge the neutrino mechanism, they don't believe that. They just argue that this could also come about from a different mechanism. And that's right. In principle, you have no first-hand proof that these signatures which shape the supernova at late times come from this initiation as predicted by the neutrino mechanism. Of course, collecting all these aspects of indirect evidence, the shape of the neutrino signal compared to observations. We have one neutrino signal from a supernova. Maybe in the near future, we have a DSNB signal, the morphology of the supernova light curve. That's indirect evidence, and you can put it together the puzzle. But it's not a proof of what is going on at the center. It's just a question of, let me say, the kind of evidence which can, in the end, be taken as a support of your theory. And it's an indirect piece in a puzzle, but it's not a direct measurement of the intrinsic physics. That's the only thing I want to say. I mean, I've been working on that for 10 years or even longer, but there's still these alternative mechanisms which people stick to. And in the end, you have no rigorous argument to fight against that. You can just accept, okay, yes, we don't have signals from the core and there is alternatives.
So one thing that I think is an issue is that people want to do joint detection studies with neutrinos and gravitational waves, but people doing the simulations only make either their gravitational wave signal available or their neutrino signal available. And so people don't have both to do a joint analysis. So that's something we need to do something about.
Both. Yeah. I'll just repeat that. We have both. I'm sure.
Yeah, I don't think that's true. Sorry, David, to jump in, but
yeah,
because I know, I mean, we're working on it, okay? Yeah. But there are the data are available from other groups.
Yeah, I'm sure it's not just. Yeah, it's not just us. I'm sure multiple groups have.
Well, it's not available to people in a public place at the moment, right? Like you said, like we can make it easy, but if we have a couple of weeks, but I've seen people write papers where they've used like the neutrino signal from a 12 solar mass model and the gravitation waves from a 15 solar mass model, because that was all they had available.
I mean, I know this because I work with Tomas and Bernard in the past on sort of collecting data from around the world, and they have a link to all of their data. So that's just an example that comes to mind. I'm sure you guys have that now, in down under, and
well, we have the gravitational wave emission.
Okay.
And I'm giving anyone the neutrino emission.
We're about to have that the neutrino data posted with the gravitational wave data on a site at Oak Ridge National Lab. So,
okay, yeah. So I want to make a comment on the reliability of the progenitor stars and reinforce what was Thomas was saying before. Rotation like convection, both of them are multidimensional phenomena. So the inclusion of these phenomena in 1D stellar models necessarily implies a number of assumptions. So my view is that at the moment the stellar models are still very limited in their prediction. For example, for rotation, what we can do is to, in some way, to calibrate the efficiency of rotation in 1D stellar models. And we do this by requiring, for example, the reproduction of some observables, the abundances in OB stars in the Magellanic Clouds or in the galaxy, or the trying to fit some ratio between the various kinds of Wolf-Rayet stars still in the galaxy. And different calibrations give very different results. At the moment, with the best that we can do, we are not able to reproduce, for example, the internal rotation velocity profile in red giant branch stars that we can obtain with the astroseismology, for example. The observations show that we should have a much more efficient angular momentum transport in the stars that we are not able to obtain with the calibration that we can do. This is one example, but there are other examples that show us that the treatment of rotation that we currently apply in stellar models is still very crude. So I am a stellar modeler, so I am talking against myself, but my impression is that we are at the point in which we cannot do much more than this in 1D, and we should move to a different approach that I don't know at the moment, but this is my view. So my warning is that we cannot believe much to the rotating models because they are still computed in a crude way. This is my view.
Thanks for the comment. One additional sentence. There's not only spin down at work, but it could also be spin up in closed binary systems by tidal effects. So there's
and we need fast rotating cores to explain, for example, gamma ray bursts. So for some stars we would need a very high angular momentum in the core. In some other cases we don't. So it's not clear.
Yeah, and just to add to that, to Marek's point earlier, the fundamental problem we have in investigating MHD-driven is that we don't know what the differential rotation profile of the progenitor is or what the magnetic fields are. Of course, we know stars are not spherical, so it's not like the grass is greener on the other side of the street either. So.
Okay, all right. I should probably connect to what Marco just said, and Thomas as well, and Tony about the challenge of knowing about rotation from stellar models. I mean, here we're facing a very difficult problem because how do you make progress? To some extent, you can hope to be informed by observables like the potential measurement of core rotation rates of a collapsing massive star, and more indirectly by measuring core rotation rates in other stars where you have some leverage on that from astroseismology. But to take stellar evolution beyond the level of 1D stellar evolution, I mean, I've been in that business for a while, and that's really hard. And you face one very important challenge, which is it's very easy to demonstrate that there's an interesting phenomenon that magnetic fields will alter the structure of the rotation profiles that you get from a 1D stellar evolution model. But it's going from there to demonstrating what the actually correct physics is that you should use to revise your 1D stellar evolution model. That's a very long haul. And that is very difficult to justify because the next steps of that undertaking are much less spectacular than the first ones. And this is something that also the gravitational wave community needs to be aware. There are, especially on the stellar evolution side, both in 1D and from the 3D angle, there are problems involved that are really still very hard and that will not just give you the next Harvard publication, that require a string of PhD students and postdocs working on that for years, making very slow and continuous progress. Another thing about Jade's comment on the neutrino and gravitational wave signals, I think I should really highlight how valuable the work by Thomas at Garching with the Supernova archive has been for the community, collecting simulation data, making it available for the community for various purposes. And I think also everyone needs to realize that this kind of building of and maintaining and curating of databases is something that is very important in its own right. Can't be done at any institution. And if the users want that, they need to realize that it's actually an extra effort for the simulators, right? It's like, well, it's something on the observational side, something like WISE-REP doesn't come out from nowhere. There need to be sufficiently large groups behind that to actually be able to collect simulation data, curate it, make databases available for the users to then do inference on it, if it's supposed to work efficiently.
So I've actually been collecting gravitational wave signals from pretty much everyone and put them all in a big repository, but it's locked behind a LIGO password at the moment because I don't have permission from everyone to share it with people outside LIGO. But yeah, so potentially if people gave me permission to make it public, I could just share it with everyone.
So on that note, can we just all collectively agree to share data and stop hiding it behind passwords and only share this with this? And once the simulations are published, just publish your signals and publish your neutrino data. Like it's weird. We're the only community who does this, and we need to stop doing this. Like, just share the data.
I think it's a good idea in principle, but I think it doesn't work just because we flick our fingers and want to do that. Because it's still, as I said, it's an effort, and you don't know what's happening to your data. So finding a format for this to happen, finding someone to curate that kind of database does require community building. It doesn't come out of nowhere. So that's if that's where you want to go, that's a much longer term challenge. It's not that you simply decide that's what you do. The environment needs to be right, and there are a lot of factors that factor into this, right? So it's things like, well, we've had that experience lots of times, right? So, well, the person who's actually produced your simulation might be a young PhD student, they are not continuing, or they might be a master student and they're not continuing. So who's going to invest into actually putting that into a usable database format? That's sometimes a challenge. Sometimes you don't have the people to do that.
Also, if I may, I know, Thomas, you're gonna, but just to comment, I think I love Bernard's idea because, as you know, Håkan, as well as anyone, the data volumes are absolutely enormous, and so the infrastructure requirements for those data volumes are, significant. So we're talking about not only, people, but also infrastructure, physical infrastructure that is quite expensive.
I'm sorry, but I have to push back on this a little bit. The neutrino signals and the gravitational wave signals, the volume of data there is not that large if you sample it on a reasonable observability.
I think there is yes, I think there are different aspects now. I actually second Hakon's comment. I mean, of course, if the person, maybe the first author of the paper or the group of authors on the paper, favors the open access, then it's absolutely natural to have this data open access. In the Garching archive, we have the policy, if the paper are published and if they are documented and if people get an explanation of the meaning of the data in a paper, we actually have no keyword to protect them. But if the data are not well explained in the literature, because what Bernhard said, students may disappear before they have published their work, or it was not the final results or whatever, there may be different reasons or some different opinions of the authors of a paper, then we have password protection, but usually we give access. But then we can actually even serve individual questions that we can. I wouldn't like to spread these data and then I get a half a dozen of emails within a month to explain every individual question about those data. Sorry, I don't have that time. Therefore, we have this password protection for data which are not really in detail explained in the literature, but we also serve requests in the sense that we don't, we answer the emails and we also give access to the data if somebody gives a real reason why the data are interesting to them.
I will also add a comment since Tomas commented on it. So there are certain data that are, of course, more easily hosted in terms of data size, but that's not generally the case. So for example, we get requests from folks focused on the mixing problem for the distribution functions. Now you start storing, the complete data from the radiation field over 1 million time steps. I mean, we're talking about huge data volumes. So I really think we have to be careful to say, well, no, the data is small enough that we can take care of this lickety split. I think that really depends on what the data is. And I think there's certainly now great motivation. I mean, we'll hear more about it this week. The focus on the neutrino mixing problem is now the 800-pound gorilla, from the standpoint of those of us who favor the neutrino-driven mechanism.
So on that point, so a few years ago, I attempted to take 20 papers and then like 80 models. And it was a trouble. Like different formats, different conditioning. I would highlight usable data. And we created tools, and then we compared them with the papers. They were agreeing, they were not agreeing. So I don't know if there's like any systematic problem with the simulations. Some stuff basically was like hardly usable. Sometimes we are analyzing like old waveforms just because the new waveforms, like we don't have time to actually process the newer one. There's like parameter space of these waveforms that we use, but it's also like very limited. So like I'm all for having a place where we have usable data, but that's something to discuss within the simulation community. How would you make it accessible? Like for us to probe, if you start to writing the algorithm to do physical inference, it's like, yeah, it's you have to first spend time to pre-process all of that, and you are not sure if you have the right thing. So yeah, I'm all for having one place with all that explanation, but yeah, that would probably be a big project. Plus neutrino, like we would like to have neutrinos. Yeah.
So I'll say this with you all as a witness, so Tony can't hold it over my head later. To Hawkins' point, it does take a lot of time to get these signatures in a way that people can actually use. I will out myself and Tony that we've been trying to get the data from the D series ready since I started my PhD program, and it's, I don't want to say how many years later, but we finally have the pipeline to do it. So now we can go through and all of the Chimera data, we're going to make all of that available. But then the next step, well, we don't have that infrastructure set up for Tornado because a lot of the modeling community is more focused on getting the physics right in the simulations and not as much looking at what happens afterwards in detail. So I would like to, put that out there for everybody. Having these signatures here, while it is a lot of work for a single student or multitudes of students over a long amount of time, it is vastly worth it because now we have 50 gigabytes of neutrino and gravitational wave data that everybody can access without a password, without anything. But it took time to get there.
Johnny, I think Johnny had a question.
Hi. So in LIGO, we have a prime directive for Star Trek fans, which is that the data we use in LIGO Virgo Kagra publications must be public. So if you want your waveform to be used in a LIGO collaboration paper, it has to be public, period. We won't use it if it's behind a firewall.
What Jay said before.
Well,
good one, Tomas.
That's a new rule. And it was also made by the last spokesperson just before they finished their term. So I don't even know if the new spokesperson knew that the old one made that rule. Marco remembers, though.
It actually comes from NSF.
Yeah.
So it will stick.
It will, yeah. Johnny?
Well,
Johnny's.
Maybe the question is, I think we all agree that this is very useful. What organization is then supposed to do this, take charge of this, right? This is a conference called, where IGWN is on the name. Should we task IGWN to do it? Right? I'm throwing this in the air, right? I think everyone agrees this is useful. Everyone agrees this is very difficult. Exactly. Well, money, time, who, and what? Exactly. But how?
I mean, these are my
right?
questions.
I get this, all of this is difficult, but if everyone really likes this, I think we better think about who and how to get the money to do it rather than just saying this is difficult.
Because we may not be able to fill this out all today. We have to continue.
Marco says it's not IGWN. So what or who else? And I guess not NSF, but.
Yeah, the My last question of the day, since we're getting close to the nominal 6:30, and I think we will generate waves of question every day. Tomorrow probably there will be another wave of questions generated by the talks that were going to be going on today. Is more like of a historical perspective. The last time we had a meeting like this, it was Caltech 9 years ago. And I remember the conversation that was, one of the conversation happening that, with all the theorists in the room, said, okay, I think we can agree on some of the features of slowly rotating progenitors. And overall, people were not very comfortable in saying that the implementation of magnetohydrodynamics was fairly robust. There were some wonderful papers by Philip Mosta trying to have the grid finer and finer. So the question I have for the theorists in the room is that, and at least that's the impression I have today, is that are we at a stage that we feel that magnetohydrodynamics is implemented in a way that we trust the result at the level we were 9 years ago for the slowly rotating or close to that?
Okay, I'm coming. My legs are starting to hurt now.
I would say very bluntly, not to the level that we want. Because quite frankly, in what